Hi, we're going to get started talking about applications of quantum mechanics. So you've done a lot of spectroscopy up to this point. Not talk while I'm attaching this because I'll probably make it take longer. So just 1 second. Okay, so molecular spectroscopy. So you've used spectroscopy in each and every one of your chemistry classes, all the way from day one, without having any understanding really of the quantum mechanics behind understanding the transitions that molecules and atoms undergo. So we're going to talk about each of the different types of spectroscopy, and we're going to start with just some general concepts of spectroscopy. So in atomic spectroscopy, you see electrons making transitions within atoms. Within molecules, though, there are all sorts of places to put energy. So the electrons can undergo transitions, the molecule can transition to different quantities of rotational energy, vibrational energy, so they'll be more complicated. So some of the general features of spectroscopy. Number one is that spectroscopy is the analysis of electromagnetic radiation being emitted, absorbed, or scattered by atoms and molecules. So this relates to the Bohr frequency condition that we've already learned about, which reminds us that anytime a photon is absorbed or emitted by an atom or a molecule, you're learning something about the separations of energy that are allowed. So remember, energies can only have discrete quantities. So E2 minus E1 will always be equal to the energy of that photon. Can't absorb and emit infinite or a continuous type of light. It's based on what energies the molecule has. So this is just something about units. We often talk about h nu. H nu equals the energy of a photon, which equals the change in energy between the two states that you're talking about. It does not look like a delta, but the frequency can also be described equally by the wavelength. So wavelength times frequency equals the speed of light. Therefore, wavelength equals frequency over the speed of light. So you could put that directly in for the nu. So you could put wavelength in. And if you put wavelength in, that's why, because I have it upside down. See over. So if I take that over there, wavelength equals speed of light over frequency. So that means that wavelength or frequency equals c over wavelength. Sorry. So you could put that directly in here. Instead of frequency, you could put in c over wavelength. That's a common thing to do. Oftentimes we actually use something called the wave number. And so the wave number, which is frequency with a tilde over it, is equal to 1 over wavelength. And so that's equal to frequency over speed of light. So you'll see all of these units, but they're all referring to just how we define the energy of light that's interacting with our system. And so there's a section that reminds you of how a spectrometer works. So all spectroscopic techniques use a spectrometer. It's an instrument that detects the characteristics of radiation absorbed, emitted, or scattered by the atoms and molecules. And because you're finding out things about the type of light, that means you're also finding out about the energy states within your molecule and atoms. So really what you're doing is using an understanding of what type of light you have and determining that experimentally, and then you can relate that to what the energies must have been. So read through this carefully. Just talks about you need a detector, you need a source of light, needs to go through your sample. There are different ways to set that up. You may or may not already have seen that in analytical. Talks about using lasers and how you might determine what kind of wavelength it is. There are lots of ways to do that, and diffraction gradient, grading is a common way. So read through that experimental understanding of spectroscopy. And now we're just going to think a little bit about how light is absorbed and emitted. And so we're going to go through this derivation. So if you have a sample and you pass light through it, you can stimulate the absorbance of that light. And so that's going to be proportional to the number of molecules you have, B, and then the density of that light. So number of molecules in the ground state, or atoms, this is Einstein's coefficient of stimulated absorption. Of stimulated absorbance, which you can get an idea from quantum mechanics. And then this is simply the density of light. With a frequency of nu that you're passing through your sample. So you pass light through your sample. If atoms or molecules are in the ground state, light can be absorbed according to this equation. But it's also true that light can stimulate the emission. So you have almost exactly the same equation that says the rate of stimulated emission is equal to something that looks the same but now it's the number in the excited state of your molecules. This is the rate of stimulated emission, so Einstein's coefficient of stimulated emission. So I'm not going to write that out. And then the density of that frequency of light. So big factor that determines how much light's absorbed is the relative number of molecules that are in the ground state compared to the excited state, because you can do both. So it is true that we also have spontaneous emission. So you don't have to have light to go through your sample in order to just stimulate the emission, and that's just proportional to how many molecules you have. So that will be equal to the number in the excited state, yeah, because it's for emission, times A, the coefficient for stimulated or for spontaneous emission, sorry. So you can show that B equals B prime. So this coefficient of stimulated absorption is equal to the coefficient of stimulated emission for the same system. So you can set B equal to B prime, and then if you add these three together, with B equal to B prime, you get the equation that your book has. So you end up with, so you have three terms. You have stimulated absorption, stimulated emission. So the overall rate of emission, no, I want to first start with the overall rate of emission, and then we'll get to the overall rate of net absorption. So that means that that's just going to be the stimulated emission plus the emission that occurs just naturally. So each of those is proportional to the number of molecules. So if I pull that N prime out front, the number in the excited state, then it will be multiplied by A, which is simply the coefficient for spontaneous emission. And then it'll be plus this, whoops, B, not beta term, and that term depends on the frequency of light because it's light that's stimulating the emission. So we have spontaneous emission plus the stimulated emission, and so that gives you the overall rate. Turns out that A is related to B prime. So if B prime equals B, so the rates of stimulated emission and absorption are equal to each other, or that coefficient, not the rate, sorry. And A equals is related to B, then we can put that back into our equation for stimulated absorption, and we can add those two together because when light's emitted, it essentially cancels some of the absorption. So if we look at the net rate of absorption, it's going to be the sum of those three terms. So it'll be the two terms for absorption, and we will end up with, that's the stimulated absorption. And that's the emission, because now we've put in this relationship between A and B. And now we can rearrange that. And from something we haven't covered yet, but we will, it's the last chapter in the book where you come up with Boltzmann's distribution. Boltzmann's distribution says that the number of molecules that will be in excited state relative to the total number of molecules will be equal to the difference between those two energy states. So as that gets bigger, this gets smaller. And then as temperature gets bigger, this gets bigger. So if you rearrange this, oops, I should first do this. So if I take these guys out front, so if B equals B prime, then I can take N minus N prime out front, and that's just multiplied by B times rho. So I'm just grouping the terms. So B equals B prime. So I have B, that term, twice. So you have N minus N1 times that term. Now you can just rearrange this to solve for what's the difference in number of excited state versus ground state. And when you do that, let's see, the best way to do that is probably just to say, just multiply through by N, and then if I want it to be N minus N prime, I can take N minus N prime on this side and N minus N prime on this side. So n is all I've added to each side, and then I've subtracted the n prime from it. So then you can group these guys out front, and you can say that n minus n prime, so the difference in the number in the ground state to the excited state is this exponential term. So I can go back and I can put that in here, and what you get for the net rate of absorption. So I'm just going to go back here to where I have n minus n prime and plug in this guy, and you are going to get equation 5 in the book. I will just say that, because you can easily see how plugging this in for this gives you equation 5. So you have an equation for the net rate of absorption, and it depends on the frequency of the light. It depends on this coefficient of stimulated absorption or emission, depends on the number of molecules in the ground state. And then this exponential term, which says it depends on how many molecules are in the upper state versus the lower state. And that's a function of how far apart the states are, as well as the temperature. So this just then helps you think about how you have to set up an experiment. So for a given energy difference, the population difference, and therefore the net intensity of absorption increases with decreasing temperature. What that really says is if you're at a low temperature, more of your molecules will be in the ground state than the excited state, which is this 1 over T term in the exponent. So you'll get more stimulated absorption because you'll have less stimulated emission. And then for a specified temperature, the population difference, and therefore the intensity of absorption, increases with increasing energy between the states. The states are really far apart. You're not going to have many populated excited states, so you'll get more stimulated absorption. So that absorption coefficient, or coefficient of stimulated absorption or emission, is related to something called the transition dipole moment, which is an integral that you would do that connects the two states with the dipole moment. So in order for light to interact with molecules, it needs to interact with an electric field. So light is an electric field, and so it will interact with the electric component of a molecule, which is the dipole moment. And so from that, you get selection rules. In, for example, vibrational spectroscopy, if the molecule doesn't change vibration or doesn't change dipole moment when it vibrates, the selection rule would say you won't make a transition in that molecule with infrared light. So a gross selection rule specifies the general features of the molecule that it must have to give a spectrum. So something like infrared, if it doesn't change dipole moment as it vibrates, you won't absorb energy in order to change that vibrational energy. So that gross selection rule would say it's forbidden. And this is specific selection rule specifies what changes in the quantum numbers may occur. So we've already looked at that. So if a photon has angular momentum of 1, selection rule is going to be that somehow the system has to change angular momentum by 1 if a photon is emitted. So same thing if it's absorbed, you'd have to increase the angular momentum by 1 as you absorbed a photon of light. So when you look at how much light's absorbed, you remember from all the way back to Chem 107, you've used spectrometers and you've looked at Beer's law. So Beer's law says that the intensity of light that comes through a sample is proportional to the intensity of the light that you hit the sample with. And then the terms that matter, epsilon is the molar absorption coefficient, which depends on the molecule and the frequency. J in square brackets is the concentration, and L is the path length that the sample of your molecule is. And so absorbance by definition is log of the intensity you shoot at it versus the intensity that comes out. And transmittance is the intensity that comes out versus what you sent in. So that makes sense, how much of it was transmitted through. So you can just rearrange that and get those two equations, which you can use to understand the relationship between the concentration and the absorbance. Yeah. So if you look at this example, it's fairly straightforward, just keeping your units straight. So I'm going to do self-test 11A.1, and it says we have a transmittance of an aqueous solution that contained an amino acid and has the molar concentration. It has the wavelength of light, and it has the path length. And it wants you to calculate the molar absorption coefficient at that wavelength and absorbance, and the absorbance of that solution. So transmittance, it tells us, is 0.14. We don't even need the wavelength of light. So L is 5 nanometers. The concentration of our amino acid is 0.1 millimole per decimeter cubed. They want us to get both epsilon, the molar absorptivity coefficient, and then the absorbance. So in order to get the molar absorptivity coefficient, I use the relationship between transmittance and 10 to the minus epsilon concentration log, which was just given in those equations. And I solved for epsilon, and I had it at first in decimeters cubed over millimole times millimeter, which would have been a fine unit, but your book says that it's more often given in decimeters cubed per mole per centimeter, so I converted it. In order to get the absorbance, I just plugged it back in, got an absorbance of 0.85. Actually, I just got the absorbance. I didn't even need the molar absorptivity coefficient. And then to get the transmittance at a new path length, I just used my molar absorptivity coefficient and plugged that in. And rather than converting this, I converted the other units. So I went from, they gave us millimole, and I converted to mole, and I converted the path length of a millimeter into centimeters and got 0.68. So it's really a problem just looking at keeping track of your units. So Beer's law comes from experiment at first, but then you can justify it in this justification. And I'm not going to hold you accountable for that, but if you want, you can read through and see how, even though it's an experimentally determined law, you can justify its form by looking at the process of light being absorbed. So this last little section just talks a little bit about some other characteristics. So we talked about absorbing and emitting. The only kind of spectroscopy that doesn't do that is called Raman scattering. And it takes advantage of the fact that when light is scattered, sometimes it might change the energy of a molecule and therefore either go up or down in energy. And you'd see frequencies of light scattered that are either greater or less than what you pass through the sample. So read through that carefully. We're going to look more at Raman after we look at vibrational spectroscopy, but just to know that it's unique in that it doesn't actually absorb the photon. It's scattered by the molecule, and in that process, it changes its energy. Another super important part of spectroscopy is always wanting to have sharp peaks so you know your frequencies well. And depending on how you set things up, especially if you're in the gas phase, you'll get often really broad peaks because of a very important thing that increases the width. So rather than giving you just a sharp peak at one wavelength, you might get a broad spectrum. And it's first and foremost related to this idea of the Doppler effect. So if you have a sample of gas molecules and they're going at different velocities, which Maxwell's distribution of speeds way back from Chem 107 taught you, that you have a gas, the particles are flying around at different speeds and you have some average speed, but some are going faster and some are going slower. And as a result of that, some of them are going towards the light and some are moving away from the light. So that changes the energy of the light that they're going to interact with. And so this equation shows you that how wide the peak is. So the change in the frequency. So if there would be one peak for a perfect transition, how broad is this essentially? Is related to the frequency, it's related to the molar mass, and the temperature that you're at. So did I do that? So we can just look at how broad it might make it. So this problem asks you, what's the Doppler width? If you have carbon monoxide and you're at 400 degrees and you're interacting with light that has frequency of 461 megahertz. So if I just keep everything in SI units, I won't have to worry. So if I change this to hertz, and then if I remember hertz is a 1/second, then that is the SI unit of time. So I can put in 2 into the equation. The frequency in hertz is 1/seconds. Put in the speed of light in meters per second. Joules is the SI unit of energy, so the gas constant in joules. And then remembering that the SI unit of mass is kilograms. So if I put in the molar mass of carbon monoxide, and I'm just approximating it to be the sum of these two isotopes, it'll be 28 times 10 to the minus third. And I get that the width is going to be broadened by 1,247 hertz. So we won't get a single frequency, we'll get that width of our peak. The other reason why the line width is broadened in a spectroscopic transition is because of the lifetime of a state. So we know that, for example, when an electron goes up in energy, as we saw in the start of this, there's spontaneous emission. Excited states spontaneously come back to ground state. And depending on the lifetime of that state, that's going to broaden the frequency of your peaks. So it's like the Heisenberg's uncertainty principle, which says the uncertainty in energy is related to the lifetime of the state. And because of that, if the energy has an uncertainty, that means the frequency at which will be emitted has an uncertainty. And so this, the broadening of the frequency range that will be absorbed or emitted, this is emitted because of the lifetime of the excited state, is equal to 1/2 pi times the lifetime of the state. So it depends on how long that state exists. So that's it for just a general look at spectroscopy. And now we're going to go through one by one and look at each of the spectroscopies and what it tells us about molecules.